let's get started. So last week we talked about L files. We talked about their headers, different headers, sections, and program headers. How to title it? Should be section and program headers. We talked about lazy binding, and this week the homework there will be one task to do lazy binding. That's all of them. Section and section headers. Okay. We also started talking about stack-based buffer overflow. Usually, that's also most of the cases. It's also called sequential buffer overflow because you can see the example we had last week. The vulnerable function is because of that string copy, and you write things sequentially. It's not like you can write arbitrary address on the stack or other places. So if you say sequential buffer overflow, most of the cases that will be stack-based. But it could be D-based as well. We briefly talked about the history of buffer overflow. We worked on how C function works, calling conventions of C. In the homework, that's worked on the faster call. And also we talked about how to overflow local variables. And in this class, we are going to overflow return address to execute a function in the same address space of your program. Not only we can execute one function using this approach, we can actually execute many functions, and we can execute functions, call functions with different arguments. So that's what we're going to do. So this is the first time we overwrite. In this class, this is the first time overwrite some control information. The data we're going to overwrite, technically it's a pointer. If you consider this is a C program, it's a pointer. It points to some other place in the same address space of your program. So this pointer points to code, not point to data. So that's why this is called a code pointer, and the attack we're going to do is called a control flow hijacking attack. And it's a big class of many different attack approaches. And what we did the last week is kind of like a data hijacking attack. So the reason we have this problem is because how the CPU is designed and how the program is also compiler is using those hardware features. So we know that on the stack we have a saved EBP or RBP, so which are the frame pointers for the previous function. And that is, since it points to other places, it's a pointer, but it doesn't really point to code, so that's a data pointer. But that data pointer is somehow related to the previous function's return address. So that data pointer can also be used to change some code pointer. Then, more directly, we have the save the EIP or RIP on the stack, which is a return address, and the return address is obviously a code pointer. So in the example we say last week, this example, last week we tried to overflow the local variable j by inputting more data that buffer can handle to overwrite j. But actually, remember, we tried to overwrite j. We also tried to do several more bytes there, more than what we need to overwrite j. And what happens is we get a segment fault, right? So today we're going to look at why we get that segment fault and how we can turn that segment fault into something useful, not just generating segment fault. So the problem we're looking at today, this is a classic security vulnerability. This is actually what Robert Morris did 30 years ago to attack several FTP servers, something like that. Yeah. So the goal here is the attacker's goal is to change the safe EIP IP, the return address, to point that to attacker's code. So when the program returns, the program will not return to where it was called from. Instead, it will return to attacker's code. So there are several steps in this attack. Today, we're not focusing on the injection code part. We will only focus on how to change the overflow the return address. So this is one of the most common vulnerabilities in C and C++ programs. There are other high-level languages. You don't need to worry about this problem. Java, Python, usually don't need to worry about this problem. But most of the systems we are using right now, we are still using low-end systems like OS, like a firmware. We're still using C and C++ to develop those systems. There is a new programming language called Rust, and Rust is supposed to be safe from this kind of attacks. And Rust is supposed to be very efficient, like C and C++. However, in Rust, there are also a lot of tricks you can use to bypass those security features. And we have seen I've seen a paper talking about a lot of the real-world Rust programs. They are trying to bypass those security features, so they still have a lot of security issues. Okay, so this is the first program we're looking at today, similar to the program we saw last time. So also I have a box here saying that if you want to disable address space layout randomization, you can do this command. For this one, I think we don't have to disable it. It's secure address space layout randomization, ASLR, is one of the security features to defeat all kinds of attacks, which we will look at probably in 2 weeks. Also, there will be homework for you, and also in my class, I will talk about how can we actually defeat this security feature. Its approach to slow down attackers, but it's not perfect. Like all other approaches, it's not defensive approaches. It's not perfect. But for today, I don't think we have to disable it. Anyway. So this is the vulnerable program we are looking at. We have our main function. Main function print out the address of a print secret function. Then we will call the vulnerable function. In the vulnerable function, we have a buffer overflow problem, like what we saw last time. Right here we have a buffer. At C code, it's 6 bytes. We need to look at the binary code to see how far is it really from the return address. Then we have this function called x, which takes input from standard input. So this function is not really checking the second command line arguments. The command line arguments are here. We're not really using those. This function is not really using those. So instead, it's taking input from std in, then it just returns. So if you gave 5 bytes, 4 bytes to this program, what will happen is this function will just return. So it will return to here, which print out IP to the full. Okay. So instead, our goal is not to native print out this IP to the full. We want to call the function print secret, which will use printf, print out animations, you made it, then it has an exit 0 there. I added exit 0 there just to make the program to exit gracefully. We can take that part off later. We can say things will be really different. Okay. So let's see how we can override this. Let's look at the function Volatile. This is a volatile function. So before we execute the very first instruction of this function, we imagine we just call here, we haven't executed the very first instruction. So at this point, our register ESP, so this is 32-bit. We are going to look at 64-bit a little bit later. 32-bit, the very first instruction is push EBP, and right now the return address is already on stack because the previous function, the main function used the call to get here. So the call instruction will put the return address on stack. ESP points to that. Then we have push EBP. So the value of EBP will be pushed onto stack. Because this is a push instruction, ESP is updated. So now the value of EBP actually is a string pointer for the main function will be on stack, and the ESP points to that. Then we have move ES. This is AT&T, so it's move ESP to EBP. Now we move ESP to EBP, so the old EBP value is lost. It doesn't matter because we already stored them on stack. Then we move the value of ESP to EBP. So both ESP and EBP point to that save the EBP address. Then we have a subtract 18 in hex from ESP. So EBP stays at the same place. ESP moves down 18 in hex like this. Then there's another instruction abstract save from ESP. So ESP moves down again. So if you ask me why the compiler generates two instructions like this instead of combining them into one, well, because we can combine them into one, it will be equivalent, right? But I don't really have the answer. The compiler just decided to do that. Yeah. So after that, we will get EBP minus E in hex. That address to the register EAX. So after that, we know EAX will also have a pointer. And that pointer points to EBP minus E. So somewhere here. Okay. So this looks like what we discussed last week. So right now, this part looks like a local variable. Then we will do another push the value of EAX onto the stack. So EAX, like I said, it's a local variable. So we're putting the local EAX points to a local variable. Like we're putting that address of the local variable to the stack onto the stack again. And that is because we are calling the function gets. And gets will take one argument, which is the buffer's address. Right? One argument, the buffer's address. So the buffer is always on the stack. So that is how we are setting up the argument for calls. Okay. So before we call this, now we know that ESP, before we call this, ESP points to here. Address, this is the address buffer, and everything else is set up like this. So we have another call. So obviously, we will go through similar things, but we don't want to go inside that. But what we know is, if we cannot go into the call to gets, we just consider this is just a one step. Then after we get out, the stack should be balanced, which means the ESP, this register should point to the same place before and after this function call. Okay. So after this function call, ESP points to the same place. Then there is another instruction inside this function to add several bytes to ESP. So we're going to move the ESP a little bit. Okay. After that, we have we'll move 0 to EAX. So EAX is used as a return value for in 32-bit programs. 64, we use RAX, the same thing. So here we are setting up the return value. Say function has a return value, and we are setting up the return value. Obviously, we're just returning 0 here. If we go back to the C code, we should be able to say here, we're returning 0. Okay? So that's why we are moving that 0 to EAX. So after this, we have the leave instruction. So leave is equivalent to those two instructions. Move EBP to EXP and the pop EBP. So the first step is move EBP to ESP. So previously ESP points to somewhere here. Now we just overwrite it. Now it points to the saved EBP address. After this, we just pop EBP. So ESP will stay here. However, EBP is changed. EBP will point to some address has a much higher number there, and that is a frame stack of the main function. Now after this, we will have the return instruction, and the return instruction has only one thing. It will pop whatever ESP points to the IP, the PC register. So here we have the return address, RET. Now after we execute that return instruction, so here the RET is the instruction ID. That RET is the return address. They are two different things. So after this, the value of the EIP will be updated to RET. Then, because the return will also pop ESP, so ESP will add 4 in this case, will point to the place a little bit higher than RET. So that is how the function works. So if we have a buffer overflow in the get function here, we can overwrite anything that has a higher address than this. So the EAX points to the address of buffer. So the buffer is only 6 bytes, something like 6 bytes, maybe a little bit bigger. But we can overwrite everything here. Okay. So we can override the buffer itself. We can override the saved EBP of the main function. We can override the return address. So if we change the address, the return address to the address of the print secret. So in theory, when this program returns, execute that return instruction, we're not going back to the main function. We're going to the print secret function. So we can try to see if we can get this work. you can say this is the program. So just to make here, and when you do make, when you compile this, GCC actually tells you this function is not secure. And also, when I compare this, I'm using the no stack protector flag here to disable cookies. But we can we will see how we can defeat cookies later. So this is a program. If we run this program, we will print out the address of our print secret, and it will ask for our input. So if we just put some random thing, it will not do anything harmful. The program just execute normally. If we input a lot of things here, we know we are going to overwrite the return address, but it will just go to all random address somewhere, and that's how we can get a segment fault. Okay, so instead of doing this, we already know the address of return secret here. Then we just try to do that and feed that address into the program. So the first step, let's accurately calculate how much padding there we need. So I'm going to do an object down to do this 32 version. Which function? So we're looking at this vulnerable function here. The EAX, we have the value. EAX points to EBP minus E. So that is the address buffer. E is 14, right? E is 14. So from the beginning of buffer to save the EBP, there are 14 bytes. So after that is 4 bytes of saved EBP, then 4 bytes of return address. Okay. So what we can do is because this program is not taking command line arguments, instead it's from standard in, so we just use a pipe to generate data for it. What's the syntax for it? C, okay. C probably is command line, print. How many bytes do we need? And 14 plus 4, which is 18 bytes. 18 bytes, then we can get something like this. So, let's see if every time we get the same address here. Oh, we actually get the same address because I already disabled the space layout randomization on my PC. Otherwise, every time we run this, we will get a different address. To make things easier for this class, I disable that. So now we just need to do after this. To the 62 55 56. So this is our input. Then we type this into the variable program, and we can say this is what happens. Instead of recording, instead of return back to the main function, we are going to this print secret. So if we can debug this, would be much more easier to understand. So in GDB, how do I give it to std in? Anyone knows? Let's see if I put that in my slides. Yeah. No, that would be command line arguments. Yeah, I want to get into std in, not the command line arguments. Yeah. Yeah, we can quickly search that. I just don't remember gdb std in. Oh, I think we can do this. So we just pipe this, we just put this into one.txt headers. Then we do gdb. We set a breakpoint at our main function, then we run. We run this, so we redirect this to std. Okay, so now we are at the main function. We just do next step to keep going into the variable function. So now we are almost at the variable function. So we step in. We are as a variable function. So we are going to call gets. So what we can do here is we can use X to examine the stack. So we are going to examine EBP and also some goods. So as you can see, right now the PC, the program pointer points to that call instruction. So we're about to call that get function. And right now, EBP points to a stack address on a stack that is actually the saved EBP of the main function. And 4 bytes higher than that, we have this 5.6 address. And that looks like a code address, 5.6. And that is actually the address of at the main function. What we can do is we can so if we disassemble the main function, we can see that address is this one, right? 6280. So that's a return address after you make the call. So everything looks good so far. Now we are going to execute that call gets, which will overwrite all of this. So we execute one step. Now we return from gets. Now we print out EBP again. You can see it has been changed. Why we're only print out 2 bytes here? So you can see we actually overwrite the saved EBP, which is this part, those 4 bytes, and we also overwrite. Is this the almost? Did we give enough input? Get enough input. So if we just continue, oh yeah, okay. So this address. Okay. This is 622D. Or is it not just we're looking at there? Yes. So previously the address was 6280, and we overwrite it to 62B or something, and that is the address of principal. So that is how it works. The 64-bit version will be very similar. Just the only difference is the address will be 8 bytes instead of 4 bytes. Also, the saved EBP will be 8 bytes. If we look at the 64-bit version, which is 64-bit version, we have x point here. The value, the address of the buffer actually is the same. It's still RBP minus E. We get that address into RAX, and RX to RDX, and RDX is the first RDX is the first argument at the 64-bit function call. So the buffer, the address between buffer and saved RBP is the same, still 14 bytes, but the saved EBP is 8 bytes instead. So we need a 14 plus 8, which is 22 bytes to overwrite the saved EBP and get to the return address. So if you run a program, we get that address. That is address of print secret. So we can do the same thing, but instead of 18 bytes, we need 22 bytes. Because save the RBP here. Then we put C9, 51, then everything just 55. How many 5s are there? 1, 2. Looks like this is good. Oh, this one I actually have cookies there. I need to disable cookies. So you can say the program print out the stack smashing detected. That is one of the different stack cookies. That's because when I compare this one, I didn't add that low stack flag. Let's see. Oh yeah, you can see here. So the 2B version I have a flag low stack protector. The 64B version actually I said protection no PLE. I think I have this flag here. Okay. Interesting. I didn't test this before I came here, obviously, so we can debug to see what's going on. So we put this into txt, then we just do a gdb this, then we set a breakpoint and Vault directly. Now we just run the program from this. Now we are at this program. We directly go to the call instruction. Now we examine the stack. Let's do 2 of this.
should be RBP in this case.
So we'll have our RDP and also the return address. 263, that's a return address. Now we call that gets, then examine this again. You can say we overwrite it. This part is save EBP, this part is the return address. Verify if the return address is correct. Disassemble that print secret function. Yeah, that's a correct address. Okay, so we just oh, but we do have that stack cookies in here. So what we're doing here, actually, this is something we're going to work in 2 weeks. What the program doing here is checking something called stack cookies, and it's a protection mechanism, and it's going to check if the stack cookies has been overwritten. And this has a function, it's a library function, stack check fail. And we're going to take that branch because we did overwrite the stack cookies. So when we do this, the program will crash, and it will just say we detect the stack buffer overflow attack. So the problem is still in that make file. Or hold on, let me just clean first. Because the program I have here, I compared last year, I think. Let's compare it again. Make OR64, I guess. Okay. Now I do this. So we still have that. So you said we should have a different flag. Low stack protector dash or. Okay, so we don't need this one. Okay. Low stack protector or like this. Okay. So we don't need this one anymore. The flag we're talking about is only stack protect, or there's no this. Anyway, okay, so the 64-bit. 64-bit GCC, no stack. It should be the same actually. That's weird. Why online PC is generating what is this? Stack cookies. Yeah, I think last year it worked. I updated my event office and switched to a new laptop. Why it's always generating stack cookies here? Okay, I will work on this offline. I don't know why. To me, it's like GCC is ignore my instructions here. I asked GCC to not generate that stack protector, but somehow it is still generating. Maybe there's a new flag for it. Okay, I will work this offline. Oh, by the way, if you want to, so those are the command line tricks. If you want to compute some data and redirect that output to another program, you just do STD in, you should use a pipe. So this is the pipe. You get the output from another program. So some of you may not be familiar with that. If you want to use another program to output as a command line element, you should have a $sign or another program there. You don't have to use Python if you are familiar with other script languages, you can use that as well. Okay, let's take a 5 minutes break from here. I actually can't work on that right now. So yeah, let's take a 5 minutes break.
I see. That's weird. Sorry to remove that. Okay, now it should work.
Now it should work. Now we don't have that. So some of the flags are conflicting. We should now use all of those. Yeah. Okay. I recompiled the program. I changed the make file a little bit. Previously, the make file was too complicated. Right now, I'm only using this low stack protector flag here. Only this one. Previously, I was fixing other things like prediction independent code, those things. So now we will have a low stack protector, and we compare it. Then we get this new 64-bit version of the program. If we do object dump on this one, you can see several things I changed actually. First is the address of buffer. It's not EBP minus, in this case RBP. It's not RBP minus E anymore. It's only RBP minus 6. So we don't have to overwrite 14 bytes in this case. And also the main function. Also the main function, it's a little bit small, but you can say after call the volatile function, we were call printf, then we were just exit. There's no previous stack, fail, or check function call anymore. So this one is not protected by the stack cookies. So what we can do is we can so in this case, we only need 6 bytes plus 8 bytes, which is 14. Then plus, oh, we don't have the address yet. Okay, so that is the address, and we type this into the program, and it works. Okay. So previous version, the problem is stack cookie. I was not disabling that. So this is how the 64-bit version is the same. Next, we are going to look at something a little bit more complicated. So in the previous example, the program or the function we return to, it doesn't take any arguments. It prints out secrets. This one is a little bit more complicated. We can overwrite a little bit more than the return address and call a function that takes an argument. I changed that print secret function a little bit. So this print secret function takes an integer and it compares that integer with a predefined value. If it matches, you print out congratulations. Otherwise, print out I pity the fool. So the idea is the same. The idea is the gets idea were override the buffer. You will override the buffer itself, the save the EBP, the return address. However, you can overwrite many more things than that. Right? So what tricky is here is we know that we can put the argument of that print secret function somewhere on the stack, but we need to know exactly where should we put it. So to find out that, we try to understand how this return works. So this return
we will do move EBP to ESP. So both ESP, EBP points to the saved address, save the EBP. Then we are going to do a pop, and the pop will not be a problem for us right now. We will pop some garbage into EBP. So after that, we will do return. Then the return address, the address of print secret will be here. ESP will be 4 bytes higher than that after this return instruction. Now, instead of a return to the original place, we return to the function of print secret. So now, at the function print of secret, it seems the stack is like this. Okay. So nothing has changed here. The difference is between here and here. We are in the first instructions of print secret, and it's going to the first instruction will be print EBP. So it will, and the value of EBP is those what we put there for A's. Then that value will be pushed onto stack. Then move EBP to ESP. So then, from print secret's point of view, its EBP starts at here. It's always factoring start at here, which is it pushes, and that is the 4 A's. And whatever is 4 bytes higher than that, it will consider as a return address. Whatever is 4 bytes higher than. But no one pushes that 4 bytes there. If this is a legit control flow, someone calls the function print secret, then someone calls that will push that return address there, right? But right now we're returning to, we're doing a return without call. We're returning to that print secret function without really making a call. So whatever is 4 bytes higher than the saved EBP, this function will consider the return address. And whatever is 8 bytes higher than this function will consider that as the first argument in this case. So let's look at this again. So we have the buffer. We have this is whatever is between the buffer and this is the EBP, right? Then this is a return address. So after this, ESP points to after return, ESP points to higher than that. So ESP, I probably draw the figure wrong here. I think the ESP should be points to 4 bytes higher than that. Okay. Oh, what I draw here is actually after this instruction. That's why. Okay. So after return, the ESP actually points to 4 bytes higher, points here. But after this instruction, we're going to push it again. That's why we get another 4 A's there. So if we want to get an address for the argument there, it should be, so this one was the old one, the volatile function. This is a volatile save the EBP points to here. So it will be 4 bytes, 4 bytes, 4 bytes, 12 bytes higher than that will be parameter 1 will be 4 bytes higher, 12 bytes higher than the save the EBP. That's how we should override that. Okay, does it make sense? Is everyone following this one? It's a little bit tricky. Okay, so this one, if we want to call the function print secret, with that argument, what we should do is we will overwrite the buffer, then the all foods save the EBP, the value doesn't matter. Then the return address of the function of all food, which we get it to the address of print secret. Then there's another 4 bytes. The value doesn't matter. That 4 bytes will be not used by print secret. Instead of print secret, we'll consider 4 bytes higher as the first argument. So that's where we should put that 1, 2, 3, 4, 5, 6 there. Okay. So let's try this. So this is a same program. We compile this. So that's the volatile function. The buffer's address is EBP minus E. That's a buffer's address. So EBP minus E is 40 bytes. So if we run this program, so this program also gives us the address. So what we need to do with this one is first of all, we override the buffer itself, which is 14 bytes. So we put 14 of A there. A doesn't really matter, you can write it. Then after that is 4 bytes of save the EBP. The value doesn't matter, so we give A to that. Then after that should be the return address of print secret. So we do okay, so if we just feed this into the program, it will still print out IP to the full, right? Oh, there's a syntax error. Why there's a syntax error? What? Oh, there's no, yeah. So we just do this, still get a print. Instead, we need to overwrite this part. So if we give 4 more bytes of garbage, then should be 1, 2, 3, 4, 5, 6, 7, 8. One more. That's this. I missed the X. 34. Okay. So if we go to this, you can say it says combination submitted. So the interesting part is you need to understand
why these 4 bytes don't matter. These 4 bytes we already know they don't matter. Why those 4 bytes don't matter. Okay.
So this is how you can
return to a function which takes arguments. And you can say, obviously, we can extend this to
other functions which take more than one argument.
this is simple. As long as you find out where is the first argument address, 4 bytes higher, just to be
The other arguments. So you will do that for your homework. So next, here I want you to think something interesting. I'm going to show you the code here again.
So this is the function print secret. All we are trying to do so far, we are trying to jump to here, return to there, and feed it with the correct argument so it can print out that combinations.
And what can we do to let it print out combinations, but we do not give it the arguments? Yeah, good. So
what we're not trying to do is we're trying to jump to here, right?
we don't have to jump to here.
So we control where we jump to. So we can jump to anywhere. So, for example, there's a compare, and if the compare is successful, we'll print out something. Otherwise, we'll print out something else. Which one is print out the combinations? Which one is print out? So here we have the compare. So this one is jump not equal. So 1252. So if the input is not this one, the argument is not this one, we will jump to here directly. And this one will print out I pity the fool. However, if we directly pull here, no, we should pull somewhere here. Because there is a push, that pushing point is setting up the argument for us. So if we directly jump to here, it will print out combinations, right? But there maybe the problem is the stack will not be balanced, because here we balance the stack. That's why in the C code I have an exit 0 there. That's why here I have an exit. Exit is not a return. So return will go back to whoever calls this function. Exit is a system call. So the program ends right here. Even if the stack is balanced, it will not give us some segment fault, something like that. Without that one, even if we can successfully print out combinations, there also will be another segment fault after that.
So let's demonstrate that first. We change the program a little bit. We comment this part out. So we only comment out exit. So it will have the same vulnerability as before. So if we give it the same exploit, is this exploit version?
address changed. Oh yeah, address changed. So we're reading to
middle of nowhere. We need to update that. 2 0D, yeah, 20 bytes. Okay.
So we change the address. So we successfully return to print secret. And we successfully give it the argument it wants.
However, that print secret function will return, right?
When it returns, we realize
Because of the stack.
so. So
Imagine this is inside that print secret function. The very top one, that's its first argument. Then this one will be, it save the EBP, right? So you save the EBP is garbage. Then it will be a return address, and which is going to itself actually. So when the print secret function returns again, it will utilize those 2 4 bytes information to return to someplace it is the I was going from it. But that where there are garbage there. So eventually you will dereference some region we're not supposed to go. That's why eventually there will be a segment fault if we do not have that exit 0 there. So with exit 0, that return instruction will not be, the return instruction will be not be executed. Instead, there will be a system call to tear down this process. Restore. That's why it's not say a segment fault. Any question there? Why are we writing 14 bytes? That's because when we disassemble that, so this is a Volatile. We can say line 1252. Line 1252. That the EBP minus E. Yeah. E is 14. Yeah. So now we are trying to print out combinations without giving that function argument. So we're not going to give the function argument. So all those parts don't matter anymore. Something like this, right? Of course, this one doesn't work. So we just need to get the address. So we cannot get the runtime address by just use an open account. So we're going to use GDB here. We use GDB to this one should be 2. So we set a breakpoint main, then we just run it. Then we disassemble EISASS, the function print secret. So now we can see the runtime address of this function. So like we said before, what we want to return to. We want to return to 0. So this is the first, this is the compare one. It compares if the first argument is this, then if not equal, you will go down there. Otherwise, you will go here in this one. I think we're going to return here. So this is the address we want to return to. And instead of here, we return directly to here. So we skip the part we are comparing the first argument. So the address is 6220. Okay.
So this is the address we're going to return to directly here. Okay, so what will happen if we directly return here? First, we're going to print out conversations, but the program keeps going. And there will be a return eventually. And that return eventually will trigger a second fault. But here we get the combinations.
Let's say it works.
Yeah, it works. Right. Combinations. Then we have the second fault. So what we did so far actually has two very important implications. The first one is you can return to any function in your address space with arbitrary number of parameters. When you override the return address, and there is a very important attack called return to libc. So instead of a return to a function you write, you can return to a C library function and ask the C library to do all kind of dirty work for you. And in C library, there is a function called system. That's not a command, there's no command for that. It's just a C library function. And use that command, system function, you can create another process or whatever. So we can create a shell, then we can fully control the computer. Another one is you do not have to return to, you do not really have to return to the beginning of any function. You can return to any place. It can be the middle of the function. In this example, we're returning to the middle of function. But you don't even have to return to the middle of function to the beginning of those instructions. You can actually return to the middle of those, any of those instructions as well. If you return to the middle of those instructions, what will happen? The CPU will interpret from that place to say what a valuable instruction it is, what a valid instruction it is. It will not be, for example, the call instruction here, let's say 27 to 32, which is 6 bytes. The call instruction is actually 6 bytes. If you interpret from the beginning of this instruction, this is a call to this. If you return to the middle of that, it will be something else. You can try that.
So this is a address. We need to do gdb main, run this, print secret. Okay, so this is a call instruction. It is here. If we, this is another gdb command, exam. You can exam using I here means instruction. We want to exam 5 instructions from this address. Okay. Oops, I should not dereference this. So
This is what we get. So if the CPU start executing from this address to 8, you will interpret everything like this. But what if there is 1 byte off?
we change the 8 to 9, then
They will be totally different instructions. But say they're still valid instructions. That's because it's a 86 instruction set. The instruction set itself is stands. Even if you just give it garbage, the CPU will consider that as valid instructions. But those instructions, for example, this one, even the first one, it may generate a second fault. It's trying to move the EAX. This is Intel syntax. Yeah. This is Intel syntax. So Intel syntax This one is destination. The second one is source. So we're moving the address, the value of the EX to this address. And look at the address. It's very possible this is the address. If you write it there, you generate the segment fault.
So we can actually try this, debug this. So instead of going to 20, we go to 21. 1 byte off, and it doesn't print out the combinations we want. It can only generate the segment fault, but this segment fault may not be the return. It may much earlier than that. So let's debug this. We do this. Go to okay, we are in the variable function. If we keep running, eventually we will get the return. Okay, so now it's a return.
Now we are returning to the middle of print secret, but not the value, the
Instruction address. We go to a SI step there. Now we jump into the middle
of print secret. And say the CPU is going to execute in. Okay, that's the one. That will generate a fault. Int is for input output for to the interceptor uses to talk with peripherals. So other CPUs will be for some devices like ARM devices, the peripherals they are handling that. So there is no special instruction like this in or out to talk with peripherals. You only have one. You only use move instructions to talk with peripherals. So this instruction is privileged. You can only execute this in the kernel.
So if we do this, it's supposed to be a segment fault, right?
So when we do this, we get a segment fault because we're not supposed to execute this. But here, those are vanity instructions. So the implication of this is there are a lot of data, kind of garbage data in the memory. And a lot of those garbage, they are actually valid and useful instructions, sequence of instructions. If we find out those sequence of instructions, we somehow weave them together, we chain them together, we can do more complicated attacks. And that is what return-oriented attacks well. So that's what we're going to look at in the second half of the semester. But you already get the idea. So the idea is if you overwrite return address, you can do a lot of not only return address, anything in the address space that is a code pointer, then you can hijack the control flow. So return address is one of the code pointers. There are other code pointers, for example, in C++. There are a lot of virtual functions. In C++, there are classes. When you program C++, you define classes. And the class, in the implementation, each class, each instance of class, they have a virtual table. And that virtual table basically is an array of return of function addresses. So each function address is a code pointer. If you can override that, you can hijack the control flow. And when you pass in program in C++, what do you usually do? You will do new class, right? To create a new class, use new class. Sometimes you make a class on stack, but more cases you probably will do a new class and make a free class. So which means that class instance will be on heap. So on the heap, there will be a lot of
code pointers. So that is called the key-based buffer overflow. So what we're doing here is stack-based. We will also talk about key-based later in the class. Okay, there are more interesting things we can do. Is what we discovered today. What if we want to, instead of return to one function, we want to return to many different functions, a chain of functions. But here, a problem is the argument, because we only got one chance to override this. Let's say there is a volatile function, Volatile, and the Volatile's stack frame looks like this. This is a buffer, which is volatile. Then we have some padding. Then we have the saved EBP here, or the return address here. We can have arguments here. If we want to pull, so if we want to overwrite the stack of this volatile, we just overwrite the return address F1, and we can give F1 arguments if we want. We can give so many arguments there. What happens is after this, F1 is F1 is a valid function, first of all, which means it has the stack, epilogue, and also productor to do all those stack balancing work. So if we override this, after the epilogue of Volatile, so the ESP will move 8 bytes. This is the key here. ESP will move 8 bytes. I will just debug that. Then EBP will be A, and the IP will be F1. So then after the product of F1, because F1 is a function and a product, then the EBP will be here. ESP at this point down there. So if we chain them together, EBP actually move the 4 bytes up. So all this is returned without faults. Then we have save the EBP here. There will be 2 save the EBP actually, because F1 will also push EBP to stack. And this one was pushed there by the function calling Volatile. This one was saved there by the function F1. And for F1, we will consider this is save the EBP, this is a return address, and this is its argument. So if we technically, if we keep doing this, then for F1, we were saying the return address is here, right? So if we only have one chance to override the whole thing, remember? So if we override the return address here to F2, the F1 will consider this as its own return address. Will go to F2. The F2, it will do the same thing. It will consider the 4 bytes higher as its own, the return address is going to. So if we are going to call, if we're going to chain a lot of functions without arguments together, this is definitely doable. We just put their return address one by one. We put F1's return address here, F2's return address here, F3's return address here, and all of them were saying this. This is a return address of F2, return address F3. So we can actually chain them together. We can chain a lot of functions together. So let's look at another example. We have 5 functions here. Each function were, so from F1 to F5, each function will just print out one word. Knowledge is power, France is
France is vacant. Okay, that's why we want to print out. We want to print out the F5 last because I have exit 0 there. But it doesn't really matter. This one just to make the program exit gracefully. So we have the volatile function, and we have the main function, which print out the function address of all those 5 functions, and we call that volatile function, and we do. So our goal is print out knowledge is power, France is bacon. So we're going to call the function f2 twice. By the way, does anyone know why France is bacon? No one knows that? Okay, you guys just Google. Knowledge is power, France is bacon. It's a classic joke. Anyway, let's go back to here. Okay, this is a program. The make file, nothing special, just no stack cookies. Yeah, I only have that flag low stack cookies. Also, I have no competition from the code, but I don't think it matters here. So if we run this program, it prints out the address of those 5 functions, and we want to call those. The first step is we do an object dump on this program. We do the 32-bit version to check out how much bytes we need to overwrite. Okay, we have the overall function here. Looks like it's still EBP minus E. Yeah, the buffer's address is still EBP minus E, so it's 14 bytes. So what we do is we do something. So this one is gets, right? So this should so first one is 14 bytes to get it to the saved EBP. Then the saved is EBP binary in this case, so 18 bytes. Then after that, we just put all those functions address together. This side shows we put all their save the EBP binary, we put all their function address here, then eventually they will be called one by one. And we can train arbitrary number of functions there. So if we do 2D 62 56 5556. Okay, so if we only call the first one, we will print out knowledge and also get a second fault.
Is it correct? 2D 16 5556.
I do not see knowledge there.
Maybe it's during the buffer before they actually print it out to the terminal. Okay, let's chain them all together. The second one is 4A. Third one is 6, 7. After that is 8, 4. Okay, let's see if it works. Okay, this one works.
I think the previous one, this one is not printing out because the function printf will not necessarily print things right away. The kernel may have a buffer or something to keep it in the buffer, but before the kernel really print out, we call the second fault. This one works because we explicitly call it exit 0. So the kernel makes sure we print out this. You can say now we can tune all of them together, right?
So function 2 is print out is, so we can do that twice to make it 2. So here we're calling the same function f2 twice. So we get the
Complete sentence. Well, we just borrow from Francis Bacon, and obviously
we can change this forever. We can take the whole thing and copy it again, or we just print out this twice.
when we're printing out knowledge twice. So we can do this forever. As long as those functions do not take any arguments, we can chain all of them together for a lot of functions.
However, things will be much more complicated if the functions we are trying to call,
they do take arguments. So in that case, we will not be able to
call,
arbitrary number of functions. For example, let's say we want to return to functions with one argument. So there are two functions. One is f1, another one is f2 in this case. So if we chain them together, remember we only have one chance to override the whole thing. So we're going to override this twice. So what we do is we'll override the return address to f1. 4 bytes higher than that will be the return address of function 2. 4 bytes higher than that will be the argument for f1. 4 bytes higher than that will be the argument for function 2. And this one will actually work. We were successfully for f1 and f2. Both of them give them one argument. This is how we're going to place them on the stack. So those are the steps. Basically, after the API of Volatile, and before we go into F1, this is what it will look like. Volatile will think this is a return address. You will not use these parts, right? You will not use this part. So down there, then in F1, you will think this is a return address, and this is its own argument. So they do not conflict. So those is not conflict. Yeah, you can see if there is one more function, there will be conflict. Because one more function, you have to put the return address here, right? But this one, this address, we already use for the argument of F1. So it's not going to work. Well, unless the argument and the address, they have the same value, that may work. In most cases, it's not going to work. There will be a conflict. So if you are returning to functions with many more arguments, then there will be more constraints. For example, if the F1 has 2 arguments, then you are going to use both of those. This is F1, and both of those will be the arguments of F1. But however, F2 will also consider this one because it's all in first argument, right? So there will be a conflict. Of course, it's the same level problem. But so this approach is not generic. I think I read a paper somewhere saying that someone designed an approach can make this generic. You can call arbitrary number of functions with arguments. I think I came across a paper several years ago, but I didn't really carefully read that. If someone finds that out, let me know. They probably use some other approach, but definitely not this one, because this approach is not going to work. Okay, so another very interesting thing we didn't talk about is the one with arguments. We only did for this one, this example. We only did this for 32-bit. We didn't do it for 64-bit. So all the demos we've been doing so far in this class, we do 32-bit and 64. But this one we didn't do 64-bit. It's because we cannot do it. So I need to think why we cannot do it with 64-bit. Yes. Because in 62-bit, the arguments are on stack and we can overwrite that. 64-bit, the arguments are in registers and we can. There's no way for us to override registers, right? So, so not only this, also return to Libc attack will be return to Libc attack basically like this. Well, imagine you are going to return to the function system and you are going to get a string like /bin/sh, a share, right? In that case, that string's address will be the first argument. And you need to give that argument to the function somehow. 32-bit, very easy, just override the stack. 64-bit, we need to place that address to RDX, which is the first argument to register somehow, right? So the approach we're going to do that is we're going to use a ROP, return-oriented programming. We're going to chain the vanity instructions somewhere in the address space. Those are called gadgets. We're going to chain those gadgets together, and those gadgets are going to move our arguments to RDX, then return to that function. So the 34-bit version of return to Libc, or general this one, we're going to look at the second half of the semester when we learn the ROP. Okay, so right now I think I have 4 cracky programs here. We already cracked 2 of those, and after this class we will do cracking 3. We will replicate what we did in class today, and also lazy binding. I think that's it. That's all I have for today. Well, it's a short class, huh? Yeah, but for today's class, there are a lot of things quite not easy to understand. So you need to spend more time on the homework. You need to debug all the program to understand how everything works. So especially those stack layout thing with arguments, without arguments. Any questions?
Okay, everything's good. See you guys next week. Yes.